check your email. I sent an email today about science fair activities. We're going to meet next week on Wednesday to plan a car wash and talk about some other business. So if you can come Wednesday in this very room at 3 o'clock on Wednesday, so check your email. And then the following Monday, we're going to have a pizza party at the planetarium show, and that's going to be in room 118, and then we'll go to the planetarium, whatever room that is. That's the following Monday, not this Monday's a holiday, so not the 11th, but the 18th at 3 o'clock. That's the only time you can do it. So if you want to come back, and there's no extra credit for eating pizza. Sorry. Then the car wash is actually November 23rd on Saturday, and you get extra credit for that. If you can help wash cars for student scholarships, you'll get 5 points extra credit for 2 hours of work. So I'm going to pass out a sign-up sheet next week for the car wash, so that everything, see who's going to attend. So anyway, just check your email. It's all there. All right. Anybody have any questions about anything in chemistry and recovery? We have one more chapter to cover, so let's see. We'll finish it next week, probably. Is it a week after Thanksgiving? Is Thanksgiving 2 weeks from today? 3 weeks from today?
3.
It's the last Thursday. It's the last Thursday of
yeah.
the month.
Is that 3 weeks from today? Or?
Yeah.
Yes.
Is it?
My birthday's in June.
3.
Okay.
1, 2.
So we'll probably have a test after Thanksgiving, I guess, because we won't finish this chapter today. We'll finish it next week. So we'll just talk about it next week. We'll see if you want to ruin your Thanksgiving or not. We can have a test before Thanksgiving or after Thanksgiving.
And then when's the final?
During finals week, whatever finals week is. I don't have any call. That's not my call. That's whatever the finals week is.
It's like the week after.
Yeah, 2 weeks.
Okay.
2 weeks after that.
All right. We're in good shape.
Okay.
Yeah, we're good. We've covered one chapter. We've got one more to cover. Although it's a meaty chapter. So try to focus tonight, because you'll go down. It'll make life easy for you down the road if you can. This chapter deals with reactions of alkenes, and this is the first chapter where you start getting overwhelmed with the number of reactions you got to memorize, and where things go. Okay, so it is some terminology that can be very confusing. So let's first of all talk about the types of reactions, broadly speaking, that alkenes, carbon compounds containing carbon-carbon double bonds, what kind of reactions they undergo. And there's one main one, and then two other ones that are more minor in scope. So let's talk about the main one first. And the good thing is they summarize all these reactions in the back of the book. And in this chapter, there's 2 mechanisms I'd like you to learn. They don't have a name like E1 or SN2 or anything like that. They're just particular mechanisms. And let's see where we get started here. Okay, so here are the classic reactions of alkenes. Compounds that contain carbon-carbon double bonds. They tend to undergo, this is YZ, they tend to undergo addition reactions. That's the classic reactions. You add 2 things called the bond. So that's where most of these chapters are going to deal with, addition reactions. But they do undergo a type of reaction called a cleavage reaction. You can snip this bond here, and you get this piece and this piece. Okay. So that's another somewhat limited type of reaction. And the third reaction is called an insertion reaction. And you can insert all sorts of things. I think in this chapter, they will insert oxygen and make what's called an epoxide. Okay. So first one is addition. Second reaction is cleavage. Third one is insertion. And by far the most important one is the first. Okay, now let me show you the slippery slope that we're heading down toward. In these reactions, the addition reactions, okay? Then we'll do some specific examples. Okay, so you can add, YZ to this, and there's four considerations you have to be aware of. Number one, which carbon gets to Y, which carbon gets to Z? Here's one possibility. But here's the other possibility. So when we do addition reactions, you got to consider who gets what. You see how those are two different products? Then the other thing to consider is Y and Z, are they both pointing up or both pointing down, or is one pointing up and the other pointing down? So, for some, but not all, for some addition reactions, there's four possible products that you have to consider. And usually one or two will be formed. You won't form all three, or you won't form three or four. It'll be one or two, okay? So that's what you're up against when you do these addition reactions. And it's especially important if your compound is a ring, because rings are not, you can't rotate about carbon-carbon single bonds in a ring. So if two groups are added, they both point up, they're going to stay up. You can't rotate them. Or a group adds up and down in a ring, you cannot rotate that. It's fixed in fixed position. So there's some terminology you want to be aware of. It's if the groups are added both up or both down, this is referred to as syn addition. See, both in the same direction, either both up or both down, same side. So it's called syn addition. If one is pointing up, the other is pointing down, like both these two cases, it's referred to as anti-addition. Okay, so just, that terminology we gang about, and that's what it means. Now, you see, well, okay, so that's one point. Now, if in many, many cases, not all, but in many cases, Y will be H. Then Z will be some nucleophile. For instance, HCl, HBr, HCN, water, HOH, or an alcohol. All of these have at least one lone pair, except this cyanide, that's okay. So all of these can add, and in most cases, when you add H plus some nucleophile, and these are the situations we'll see in this course, in most cases, you got to decide who gets the H and who gets the nucleophile. Well, the carbon that has the most hydrogens gets the H, and the other carbon gets the nucleophile. See, so if I'm adding these guys to this carbon has two hydrogens, this carbon has one hydrogen. So the hydrogen will go here, and the nucleophile end up there. That's in most cases, that's the case. See? And a fellow by the name of Makovnikov discovered that. So it's called Makovnikov's rule, or Makovnikov's addition. And the trick to remember it is just whoever has the most hydrogens, that gets the hydrogen. The other carbon gets the other group. So pretend Y here is H. In fact, let's get rid of this. Let's put H nucleophile. So here's your H and your nucleophile. Here's your H. that sounds. I'm sure you know, hopefully you know what this is about. Okay, so this H1 ended up on the carbon into most hydrogens. So this is called Markov-Markov orientation, or sometimes called Markov-Markov addition. And nobody wants to write a Markov-Markov too long, so they just go Mark orientation. This is also Markov-Markov orientation. So don't let the names fool you. When they say Markov-Markov orientation, that just means that when you add H nucleophile across the carbon-carbon double bond, the carbon has the most hydrogens, that will end up with the hydrogen, the other carbon is the other group. That's the typical addition. In most cases, if you got a guess addition takes place and you have Markov-Markov addition. Okay. But chemists sometimes don't want the H at the end, they want it in the middle, so they have developed special reagents to go against nature, so to speak. And if you get the H over in the middle carbon and the nucleophile at the end, they refer to that as anti-Markov-Markov orientation. Chemists want to be able to put that H wherever they darn well please, and put the nucleophile wherever they darn well please. So I mean, they want to be able to control where these guys add. So normally it doesn't go anti-Markov-Markov, but chemists have figured out ways to make things that are not normally easy to make. Okay, so anyway, there's no relationship whatsoever between syn addition and anti-addition, well, let me rephrase that. There's no relationship between syn addition and Markov-Markov orientation. You can have syn addition and anti-Markov-Markov orientation. You can have syn addition and Markov-Markov orientation. See, there's no relationship between these two either. You can have anti-addition and anti-Markov-Markov orientation. You can also have anti-addition to Markov-Markov orientation. So those are two different concepts. When you talk about syn or anti-addition, you're talking about which directions in space do these groups point. Do they both point up, or is one up and the other down? So that's syn or anti-addition. Which directions in space are they pointing? When you're talking about Markov-Markov and anti-Markov-Markov addition, you're saying who gets which group, who gets the hydrogen, and who gets the other group. These are two different compounds. See this? Markov-Markov orientation gives you this compound, where the nucleophile is in position 2. Anti-Markov-Markov gives you this compound, which the nucleophile is in position number 1. So these are completely different compounds, different structural isomers, or what they call constitutional isomers. These have the same bonding sequence, nucleophile in the end, nucleophile in the end, but they point in different directions. See, so these are stereoisomers. Remember, stereoisomers, same bonding sequence, but things just point in different directions. And again, when you do these reactions, you will either get one of these 4 phospho products or 2 products. That's it. If your mechanism involves a carbocation, you'll get 2 products. If it does not involve a carbocation, you usually get 1 product. Because carbocations are flat, like this, and that's formed in the first step, the slow step, and then the nucleophile adds in the second step, the fast step. If you're adding a nucleophile to a flat carbocation, it can go in from one side or the other side. See? So you'll get both a syn addition and anti-addition. Okay, if it's a carbocation. If it's not a carbocation mechanism, then usually the nucleophile just comes in from one side or the other. So you'll either get syn addition or anti-addition. And carbocations are kind of a pain. They tend to rearrange, they tend to undergo side reactions. So chemists try to avoid carbocations if possible, especially what you're working with. It's expensive. You don't want side reactions. And so you're going to use other reagents to avoid carbocations because they can give you side reactions. Okay, so let's take the 2 mechanisms you need to learn involve adding either these guys to an alkene or these guys. That's the only two mechanisms you have to learn. The other ones, some of them are kind of complicated, okay? Now, these are strong acids. If you want to add these across a carbon-carbon double bond, you don't need to add anything else. They'll react, okay? Alcohols and water are weak acids, so you have to have sulfuric acid if you want this reaction to take place. So you'll see HCl, HBr, HCN all by itself. Mixed in with an alkene, you get a product. If, on the other hand, you're reacting the alkene with water or an alcohol, you're going to have sulfuric acid there to kind of get the ball rolling. Okay, so let's go over. I can take any one of these. Okay, so think. Don't be specific. Think any one of these will work. Let's take HBr as our example. Okay. What happens when HBr? Oh, by the way, before I forget, this is in your book on page 395. This just kind of summarizes the addition reactions. These are the addition reactions. Okay. So we're going to discuss, first of all, this one, HX, where X is a halogen using chlorine or bromine, and then water, and then we'll discuss the rest of this. Okay. So those are just the addition reactions that we're discussing. And a carbon-carbon double bond is a rich source of electrons, so it is a nucleophile or a base. These electrons are loosely held, they're high electrons. So if they see a positive charge on a carbon, they can attack it, and it's called an electrophile. If they see a positive charge on a hydrogen, they'll attack it. This is called a base, okay? So that's usually the first step with these examples is this swings out and attacks a carbon or a hydrogen. And what you learned before helps to explain maybe why you get typically McCall-McCall addition. Okay, so here's HBr, and you see this dot? That's the pivot point. See this dot right here? So this can swing out like that. It swings out this way, attacks this hydrogen. This leaves. This is easy to break because this is a strong acid. You'll get a positive charge here. Okay, so that's the first step. And then the second step is nucleophile attacks. So it's a proton transfer and attacked by nucleophile. But let's take this, see this little dot here, see this? Let's make that the pivot point. Let's swing that out this way, attack this hydrogen, and form a bromide ion, and then this can attack this, can be a product. So do you see this, why this is McCall-McCall addition, this is anti-McCall-McCall addition? This carbon has one hydrogen, right? This, and this carbon is none. Okay, so if the body pair swings out like this, do you see you get this carbocation? And if it swings out this way, you get this carbocation. Okay, and do you see why this is more stable than this? You see the difference between these two? What degree carbocation is this? First, second, or third degree? This carbon right here is attached to 1, 2, 3 of the carbon, which is third degree carbocation. This carbon is attached to 1, 2. See? So, for what you learned in previous chapters, third degree carbocations are more stable, they're formed faster. This is why you get McCall-McCall addition, because if it swings out like this, you get the positive charge here, which is attacked by a nucleophile. If it swings it out like that, you get a higher energy, low probability carbocation, and you get this. So this doesn't happen for the next two here. And so that's the reason when you add H nucleophile across a carbon-carbon double bond, the carbon has the most hydrogens, picks up that hydrogen. See, if this carbon here picks up this hydrogen, I get a third new carbon cation, which is very stable, it's going to be attacked. Okay? So that's just, that's the bottom line. And so I will give you a reaction, ask you for the mechanism. Okay? Let's give you one. Now, anytime I ask you for the mechanism, I'm going to give you the Sturman 2 and thrust, right? You won't need to. Okay, so let's give it the top. The top one is a no-no. Okay, let's do the bottom. This is what you did in lab, those of you who did lab. Actually, we did an alcohol, but we didn't use that, did we? Okay. Okay, can you give me a mechanism? Yes, and that could be, this is HCl, it could have HBr, HCN, those strong acids give you the same mechanism. First, it's a two-step process. First step is the slow step, formation of carbocation, 2 arrows. I'm looking for 2 arrows. Second step is the fast step, and that's 1 arrow. Now you can't do it all 3. You can't draw all 3 together because it's not a single-step process. It's a multiple-step process. And again, this doesn't have a particular name. It's not SN1 or E1. So this is an addition reaction. So this is going to be my pivot point. So I can swing this out here. And this swings out that way. Then I end up with a third degree carbocation and CO minus. Okay, so that's the first step, slow step, 2 arrows, and then the second step is fast. This attacks carbon ADH product. Okay, so that's a fairly straightforward mechanism. Just be able to do that with HBr or HCN. And notice what we started with. This carbon has a hydrogen. This carbon doesn't have any hydrogens. So when you add HCl, the carbon has the most hydrogens, ends up the hydrogen. The other group gets a nucleophile. That way you form a more stable carbocation. Okay. So again, it's a 2-step process. Here's the same mechanism again on page 399. Exactly the same. So first step, 2 arrows, proton transfer. Second, forming a stable carbocation. Second step, attacked by a nucleophile. And so here you have the energy level diagram. So it's a 2-step process. Formation of carbocation is always a slow step. So this swings out, form this, then this attacks and likewise. Activation energy is highest for the formation of carbocation. Second step is really pretty fast. Now, you don't need to worry about syn or anti-addition if a carbocation is formed, because remember, if you form a carbocation, it's flat. Here's the carbocation. The hybridization is sp2. You get an empty p orbit. So this guy can come in from one side or the other side. You have a choice. So you're going to get both syn and anti-addition. Put down any product you want to. It's the right answer. Okay. But you have to make sure, while it doesn't matter, you get both syn and anti-addition. You got to make sure you get Markovnikov orientation. Make sure that the carbon has the most hydrogens, gets the hydrogen, and the other carbon gets the other group. See? So starting with this carbon doesn't have any hydrogen, this carbon has one hydrogen. So this carbon is going to end up with the hydrogen, and the other carbon will end up with the nucleophile. All right, now, what about if you have the nucleophile is one of these guys, which I'm hiding from myself, I can't find it anymore. What about if it's water or an alcohol? Those are weak acids, okay? They're not going to protonate the alkene. And the first step is protonation of the alkene. So if you have water or an alcohol, you have to add sulfuric acid. And you're going to get addition. And the carbon has the most hydrogens, the one on the far left ends up the hydrogen, and the other carbon ends up the OH. And you're going to get, so this is Markovnikov addition, and you're going to get both syn and anti-addition because it's going to go through a carbocation again. Okay. So here's the mechanism. Again, it's one extra step. At the end, there's an extra step. So this is 3 steps, not 2. First step is the same. Let's put the hydrogen here. Here's my pivot point right here. So this is going to swing out like that. Form a more stable second degree carbocation. Okay, so that's step number 1. And that's just 1 atom because we got H plus floating around. Usually we had sulfuric acid. Okay, so that's fine. All right, then second step is now the nucleophile water can attack. That's step 2. This was step 1. This is step 2. After you get attacked in step 2, we have this. Then most chemists are lazy. They just do this. Now again, if you want to be a stickler for details, water is what pulls it off, but I don't care if you put that in there or not. Water actually, pulls out that hydrogen, but chemists don't really care. They'll just say hydrogen leaves, just as long as you have a pair of electrons going back onto the oxygen, and you put minus and plus. So if you want to leave out this part here, that's perfectly fine. Anyway, with the alcohol or water, you first protonate, just like before, except this is not strong enough to protonate an alkene. So you have an acid. So you have an acid, that protonates the alkene, just like before. Second step is the same as before, nucleophile attacks. But then we have an extra step. This is a neutral nucleophile, so it has to lose a hydrogen ion to give you your final product. Okay, so those are the only 2 mechanisms that you need to know for this chapter. Addition of HBr, HCl, or HCN, 2 steps, 2 arrows in the first step, 1 arrow in the second step. And then addition of water or an alcohol across an alkene, that will be 3 steps, okay? First step, 1 arrow, second step, 1 arrow, third step, 1 arrow. That allows you to go from this picture to this picture here. Now, pretty much anything water can do, alcohols can do also. So HOH is water, but this also works with an alcohol. So we have HOR. Okay, so you'll see this reaction. You don't see it in this chapter, to be honest with you, but you'll see it in a later chapter. It's a way to make ethers. Okay, any comments, questions so far? So there's like 5 reactions, but they're all basically the same. H goes on the carbon with the most hydrogens, the nucleophile goes on the other carbon. Don't worry about syn or anti-addition under these conditions. Just Markovnikov or anti-Markovnikov orientation, that's the key. All right, now, chemists don't like carbocations because, again, they do all sorts of weird side reactions. So they've come up with a way to add water across an alcohol across a carbon-carbon double bond, and you don't have a carbocation. Because remember, a carbocation can rearrange. It can also add to an alkene. It's just a bunch of annoying things it can do. Okay. So this is a toxic reaction because you got to use mercury. But if your alkene is very, very expensive, you don't want side reactions taking place. You don't want a carbocation mechanism operating. So chemists have developed a mercury compound that can add either water or alcohol across a carbon-carbon double bond, and you don't get rearrangements. You don't get side products. So your valuable starting material is not lost to side reactions. However, these conditions you get anti-addition. Since you don't have a flat carbocation, the attacking nucleophile can only come in from one side. So you got to remember, if you use these special conditions, you will get anti-addition. You still get Markovnikov orientation, but the addition is anti. Let me see my notes over here. Okay, so here it is. Anytime you see number 1, number 2, that means this reaction does not occur in a single step. You gotta put some reagents in, like number 1, mercuric acetate and water. A reaction takes place. Then after that reaction takes place, then you put in the second set of ingredients. You can't mix these together, 1 and 2. They'll react with each other. So sometimes it's a real pain. You got to add a set of reagents, get one reaction, then add another set of reagents to get another reaction. And acetate is this. This is the acetate ion. It has a charge of -1. And mercury, of course, this has a charge of +2. There's 2 of these guys. I can't write any other side. There's 2 of these guys. So they just call this the OAC ion. Okay. So it's just called mercuric acetate and water. And what happens? Mercury forms a bridge, not a carbocation, but a bridge. See this? Across the double bond. It's an insertion type reaction. Okay? And so you don't get a free carbocation that can rearrange and do bad things. And now the nucleophile can attack. But the mercury's in the way from the top side, so it can only go in from underneath. That's it. Okay? It can't come in from the top. Now, I have water attacking this carbon and this pair of electrons leaving. Why not have water attack this carbon and have this pair of electrons leaving? You're going to get a different product, see? But you only get one carbon attacked. And here's the rationalization after the fact, of course. This carbon has 4 bonds. So in advance of this attack occurring, this bond has to start to break. So these electrons start to leave and go toward the mercury. You start to develop a partial positive charge right here. Now, what degree carbon is this? First, second, or third degree carbon? How many other carbons is it attached to? The third degree carbon, right? Okay. All right, so here's our hand waving coming up. If it attacks that carbon, in advance of attack, this bond starts to break. You have a partial positive charge in this carbon. What about if the water would attack the other carbon instead? Well, this does not happen. Because if it attacks this carbon, then this bond has to start to break in advance, and you have a partial positive charge on this carbon. But this is a second degree carbon, see? So full-on carbocations are stabilized by R groups. The more R groups you have, the more stable it is. Developing carbocations are also stabilized by R groups. So the rationalization used is when this attacks this carbon, a partial positive charge has to develop on the carbon that's attacked. This carbon is a third degree carbon, this is a second degree carbon, this can accommodate a positive charge better, so the attack only occurs in this position here. And the attack has to come from underneath. Okay, so you get this. Then, this mercury is replaced by hydride. How does it happen? Nobody knows, nobody tells you. They're probably not sure the mechanism, okay? So that's why we're not gonna worry about the mechanism per se, because it's not well understood. They have their ideas, and they have their thoughts, but it's not conclusive yet. But you do get McCormick orientation. Look what we started with. We started with these guys. So this carbon had the most hydrogens. It gets to hydrogen, and it's not obvious. Let me circle this. This is anti-addition. You can't really tell here because the two groups are the same, so it doesn't really matter. But in this case, this hydrogen and this hydrogen were added, and one points up, the other points down. Okay, so the water comes in from underneath, breaks this bond, forms this, and then by some mysterious sequence of events, this is replaced by H minus. Get that? Okay. Now this is toxic. It's nasty. You got to do it 2 steps, but you get high yields. So if your starting material is very expensive, very valuable, and you don't want side reactions, you don't want carbocations, this is the way they do it. Okay. This mechanism will not be asked of you. Okay. Instead, I'll just ask you to do the products. So I'll give you the starting material, the reagents, you tell me the products. Okay? That should be straightforward. Anybody have any questions with that? So it's just another way. Now, they don't talk about this in this chapter, so let me just briefly mention it. Anything HOH can do, HOR can do also. So in a later chapter, you're going to see the same reaction. Instead of using HOH water, they'll have HOR. So you'll have an R here, an R here, and an R here. And so you're going to make an ether. So just file that away for later, for safekeeping for next semester. In this chapter, they just use water to make the mercuric acetate. I don't think they use an alcohol. They might, but I don't think they do. All right, now, suppose you don't want the hydrogen to end up here and the OH or OR. If suppose you want anti-McCormick orientation, you have to create without a paddle, and up until recently, the answer is yes. McCormick orientation is the natural way things go. But chemists have come up with a way to add the H and the OH, or the H and the OR, in the anti-McCormick fashion. Okay? And again, they're not sure of this mechanism either, it just kind of works. So you just got to remember, some sort of the same starting material. Same starting material. They're using BH3, that's nasty, nasty stuff. It's very reactive. It's a gas, a very toxic gas. Boron doesn't have 8 electrons, but if you mix a tetrahydrofuran, it's called THF, it forms a nice stable complex. So this stuff is explosive by itself. If you mix it with a solvent, tetrahydrofuran, it forms a nice stable complex, but you still got to be very careful with it. So add that, and you get a 15-arrow mechanism for the first step. We're not going to worry about memorizing that first step, 15-arrow mechanism. Second step, they have no idea pretty much what happens. They think it might be a free radical mechanism. They're not really sure. They say they're not sure. So this is another one of these reactions. Don't worry about the actual step-by-step sequence. There's just too many steps involved, and it's not understood clearly yet how it happens. So, but you cannot just mix everything together. These guys react to each other. So first you mix this with this, get an intermediate product. Then after the reaction is over, then you dump in this, and you get the final product. So, do you you see the difference, take a close look at the difference between this. First of all, I neglected to tell you, the H and the OH are on the same side. See? So this is the H that was added. Oh, no, this is the H was added. This is the OH. Okay, so we started with this and this. The carbon had the most hydrogens, did not get to hydrogen. This carbon got to hydrogen. And the other carbon got to OH. So that's why it's anti-Markovnikov orientation. See? And the two groups that were added, H and OH, both point down or both point up. So that's why this is syn addition. Okay. So start with this, add these reagents, you get anti-Markovnikov orientation. H is over here and OH is over here, and they both point in the same direction with division is syn. If you use these reagents on top, and let's say we have water as our nucleophile, let's get rid of the alcohol for now. Okay, so let's go back to water. Here's your final product. You get Markovnikov orientation. The carbon had the most hydrogens, got the hydrogen, and the addition is anti. This and this point in opposite directions. So it's a mess, isn't it? With these special reagents, typically you will get either syn or anti-addition with a special reagent. If you just add water and an acid, you get a carbocation, and you get both anti and syn. So just remember, if you have a carbocation formed as an intermediate, you're going to get a mixture of the left-handed and a right-handed molecule. You get two products. But if you don't have a carbocation, then usually attack just occurs from one side or the other, and you'll get either syn addition or anti-addition. And this is extremely useful for chemists because this is how they design pharmaceutical drugs. They may want the H on one carbon and the OH on another carbon, and they may want it to point in a certain direction. So they have special reagents that allow them to direct who gets which groups and which directions in space do they point. So this is something that takes years and years of trial and error lots of times to figure these out. Now again, these reactions are summarized for you at the end of the chapter. So I'll show you. All right. Now let's do something easy. Let's add the same thing across a carbon-carbon double bond, like hydrogen and hydrogen. See, you add the same thing, you don't need to worry about who gets what, because you're adding the same thing to both of them. So Markovnikov, anti-Markovnikov considerations go out the window. Okay. All right, let's see what I do. By the way, if you just add water and an acid, I don't think I showed you this. If we just add water and an acid, okay. Another way of saying water and an acid is H0 plus. So none of those special reagents, no mercuric acetate and sodium borohydride, no BH3 and tetrahydrofuran and sodium hydroxide and hydrogen peroxide. Just a regular water and an acid. You get the carbocation. Then the water coming from one side to the other side, so you get a 50-50 mixture. Okay, so that's when you typically get the two products, and then you got to separate those two products. That's a pain. So that's another reason for using these special reagents. You only get one product. All right. Okay, hydrogen gas. Adds across the carbon-carbon double bond, and typically it adds syn. They go to the same side. Okay, that's typically how it works. So if you have something like this, and you add hydrogen gas, and the catalyst is usually palladium, platinum, nickel, you're gonna get not the cis and the trans, but only the cis isomer. That's it. Typically, they both add the same side. Okay? And you need a catalyst for this to happen. And what a catalyst does, it weakens the hydrogen-hydrogen bond, makes the reaction go a lot faster. This bond is not that easy to break. But if you have a catalyst, solid catalyst, what happens is it tends to bind to the catalyst and break these bonds. And now carbon-carbon double bond can come in and hitch up to one of these and the other. Hitch up to both of them. And it kind of floats away. And then another hydrogen gas moves in here and you form this and it moves in again. So it's useful to have this. The mechanism is not probably entirely understood. Those dark smears are the the catalyst, nickel, platinum, platinum. And the hydrogen atoms just sit there, and this comes in, binds one and binds the other. And it drifts off into space. Okay, so unsaturated fats have carbon-carbon double bonds, and those are supposedly healthy fats. Saturated fats don't have carbon-carbon double bonds; those are the bad ones. Okay. The thing about unsaturated fats, they tend to go bad quicker. They don't have a long shelf life. So if you get rid of some of those carbon-carbon double bonds, you increase the shelf life. So like Twinkies can stay on the shelf for a year, be perfectly fresh, because they hydrogenate. They get rid of some of those carbon-carbon double bonds by hydrogenating them. The other thing about unsaturated fats, they tend to be liquids and runny. So if you want to make icing or fudge, you don't want the icing all runny and everything. You want it to kind of semi-solid, and you want it to melt in body temperature, melt in your mouth. So they get rid of the carbon-carbon double bonds in liquid vegetable oils, and they make Crisco, which is solid and holds its shape a lot better, and it has a longer shelf life. So for texture purposes and for shelf life, they get rid of some of the carbon-carbon double bonds. They add hydrogen across it, just like here. And that's why you'll see partially hydrogenated vegetable oil. They don't get all the double bonds because then it'd be too hard and brittle, but they get some of them. And natural oils, natural fats have double bonds in them if they're unsaturated. And these naturally occurring double bonds on the top picture there. These are those sister trends. They look cis, yeah. See, here's the double bond. This is going up, this is going out. So naturally occurring fats, the double bonds, and this is a fat molecule. Okay. The fat molecule has cis double bonds. Okay, this has 3, so this is a polyunsaturated. If it's got double bonds, carbon-carbon double bonds, it should be unsaturated. Anyway, when you hydrogenate these, when you partially hydrogenate, you don't get them all. You get maybe 1 or 2 of those things. But in the process of hydrogenating this, sometimes under these conditions they flip and become trans instead of cis. So they can knock out, they can add hydrogen gas and a catalyst. And they're going to knock out some, but not all of the double bonds. So notice it was 3, now there's 2 gone, 1 left. So it's partially hydrogenated, but in the hydrogenation process, the cis isomers turn to flip over under the conditions of acid catalyst, and so you get trans. See, this is pointing down, this is pointing up. You get trans fatty acids, and they're unnatural fats. Your body doesn't know how to deal with them, so they tend to accumulate in your arteries, and that's what some cause heart disease. So anyway, that's what I call trans fats. So don't go eating McDonald's, fried chicken, you get the fat trap. But pretty much from all the publicity, the negative publicity, these companies now quit using trans fatty acids because it's this bad rep. So that's, now it's not as bad as it used to be. But anyway, if you buy margarine, you're getting trans fatty acids or Crisco, things like that. So they still sell it. Let's see. Anyway, so you can add hydrogen across the carbon-carbon double bond, and the addition is usually going to be syn addition, right? Same side. All right, what else can we add across the double bond? What about bromine? We did that in the lab. Let's do bromine. Remember in lab, you've done this, how many times have you done this? 3 times now, you take the lab. When you isolated limonene, which contains a carbon-carbon double bond, you added bromine to see if you had double bond. When you made cyclohexenol, the 3-methyl-cyclohexenol, you added bromine to it. And then this week you made the pentene derivatives and you added bromine, and bromine color disappears. It's halogens like bromine and chlorine and iodide react across carbon-carbon double bonds. Okay. Now you don't need to worry about who gets what, do you? Because you're adding the same 2 atoms across the double bond. But you got to know which direction in space they point. And it turns out the addition is anti when you add a halogen. Okay. So chemists have dreamt up good reason for this. Why is the addition anti? When you add a halogen, and the reaction is pretty fast too. You know, you don't have to heat it, and it goes right in a shot. So you have a carbon-carbon double bond. X2 is either chlorine, bromine, or iodide. You get this. Because you don't need to worry who gets what, because they both are getting an X, a halogen. But you have to know if it's anti or syn addition. All right, so here is the rationalization. I drew in just one over there. So this swings out, Texas going, this leaves, and at the same time this does it. What a mess. This is my pivot point, okay? All right, so see the fasten when we pull on you. See what happens. Okay, this is called a bromonium ion, not a free carbocation. Okay? So this is not flat. Okay? So the bromine can't come in from either side because this crowding on this side is kind of big. Bromine's kind of big. So it comes in from the opposite side. So you get antenna. So if you saw something like this, and I gave you bromine, or chlorine, or iodide, and you give me the product. Compare this to if I give you a hydrogen gas and a catalyst. Compare these 2 products. In both cases, you're adding the same thing across the carbon-carbon double bond. In one case, it's Br and Br. The other case, it's H and H. Because you've got to try to remember as best you can. The H ends on the same side, both down and both up. So that's syn addition. Whereas the bromine as across it forces the issue, so to speak. The intermediate, I'm not going to answer for this particular mechanism, but the intermediate might look like this. See, the bromine, the negative charge has to come in from behind and attack this, and this moves up here, and it pushes this methyl group up. It attacks this, it's like turning inside out, inversion, you hear so much about it. So you get an inversion, it comes in from behind like that. All right, so with the bromine and the H2, you don't have a free carbocation, so you don't get both syn addition and anti-addition. You just get one. All right, so there's a lot more details, drive me nuts to get this straight. Okay, now if this mechanism is true, and by the way, I'm not going to ask you to reproduce this particular mechanism, okay? But if this mechanism is true, then any negative ion that I have, any nucleophile, doesn't have to be negative, any nucleophile, any has a lone pair, could also conceivably attack this. It doesn't have to be Br minus. So that opens up a whole range of complications for us, because besides having this attack, we can throw in a bunch of sodium chloride, a whole lot of sodium chloride. And so besides having just a little bit of bromine, so you'll have a small amount of this present, but you'll have a large amount of chloride, see? Because we don't get extra sodium chloride. So we have 1 mole of this and 10 moles of this. This doesn't react. Okay. Sodium chloride will not react with the one. But bromine will, and once it forms this bromonium ion, if you have a 10 of these or 1 of these, there's a good chance that this is going to attack instead, see? So you can get a mixture, okay? Now, this is a symmetrical alkene, so it doesn't matter. This chlorine can attack this carbon or this carbon. This bromine can attack this carbon, this carbon. It doesn't make any difference, right? Because this is symmetrical. But suppose it's not symmetrical. And suppose chlorine's attacking. Okay. Can you predict who ends up with the bromine and who ends up with the chlorine? In other words, if I give you this reaction, let's make one of these methyl groups an H. And let's add bromine and halogen. This is not step 1, step 2. Bromine will not react with sodium chloride. So I just toss everything in the pot, okay? And the sodium chloride will not react with double bond, but bromine will. So I did this intermediate. And I have a bunch of chloride ions, so now your job is to answer the question, does it attack this and this vibrates and this electrons go here, or does it attack this carbon? Now this carbon is going to be attacked, already has 4 bonds, see? So in advance of this attack, just as this chlorine is attacking, these electrons have to start to leave, go to its positive center. See, in advance of this attack, or as this is starting to come in, this has to start leaving in advance. Okay? So you get a form of partial positive charge when it starts to leave here. If this bond breaks, if you attack towards with this carbon, these electrons start to leave, and you start to form a partial positive charge here. So again, you've got to predict who would rather have that partial positive charge. that's where the nucleophile is going to attack the carbon that has the greater or the slight partial positive charge. And I think you can see that the attack will occur here because as these electrons begin to leave, go to this positive center, you develop a partial positive charge on the third lead carbon. If these electrons leave, you develop a partial positive charge on the second lead carbon. So that step to the left is not going to be favored. So in fact, this is just the intermediate, of course. In fact, you mix these guys together, what you end up with is, let me show you this way. Bromine will be here. And the CO will be here. And the opposite side is anti-tide. This comes in from underneath. See, it doesn't come in from the top. You get it from the same side. It comes in from the underside. So this is anti-addition. This is pointing one direction, this is pointing the opposite direction. So if you just see bromine by itself, you know you have bromine, bromine. If I didn't have NaCl, then I'd have bromine here and bromine here. It would be anti. But if you see bromine and NaCl or NaI or NaF, then besides having bromine, you could have some other halogen pointing in the opposite direction. Now, I'm not going to ask you for any of these mechanisms. I just want you to kind of see how you arrive at it. The driving force is the same. If you get a form of positive charge on a carbon or a partial positive charge on a carbon, the one that can handle a positive charge always is the force. Let's do one more. A different one. Instead of adding chloride, let's add sodium hydroxide. And these are fine. You don't need to do it in two separate steps. Bromine and hydroxide don't react with each other. So that's why you don't see step one, step two. Just and it's understood they're going to have a large excess of sodium hydroxide, so that once the bromonium ion is formed in a slow step, there's going to be a lot of hydroxide there just hanging out waiting to attack. Now, these types of problems, I'm not going to ask you for the mechanism. I just want you to tell me what is the product. What the product is. I have chosen myself. Two things I'll be looking for. The bromine's on the left, and the OH is on the right. And they point in opposite directions. So as long as, as long as they point in opposite directions, I don't care. As long as the bromine's on the left and the OH is on the right.
So why does it matter what side it's on?
Well, because it would be a different product.
Oh.
See, read different compound, we did this. So, those are two different compounds. The one on the left is one hydroxy, one methyl, two bromine, and one on the right is one bromo, one methyl, two hydroxy. So they're different compounds. They're different, they're put together differently, so they're constitutional isomers. So this would not be entirely correct either. We did this as kind of. This is not good either because they're not pointing in the right direction. So it's a lot to keep straight there.
If BR is on top instead of bottom, does that matter?
No. So this is acceptable, but you could also put the BR here and this here, and then of course put this here and this here. And actually we get a mixture of those two isomers. That would be stereoisomers. And that would be a pair of enantiomers. So you get a pair of enantiomers. Okay, now this is kind of harsh. You don't really need to do this. You can just use water. So you'll see a halogen in water because water can attack the bromonium ion. So you have the bromonium ion. In the first step. And water will attack. So you probably won't see sodium hydroxide, you'll see water. Then after the attack of water, then you do as an H+. Okay? I'm getting used to that by now. Then minus H+. So just be a little on the alert. You probably won't see. You probably won't see sodium hydroxide. You'll see water. I mean, you might see some hydroxide. You don't need that's overkill. Just a halogen and water. Okay. That works fine. All right. Let's see what else we have. You probably have a need for a break. When we do that, when we take a little break, and then I'll show you some more exciting reactions. It's going to feel like another. This is a grind, so I know we. So let's do this. Let's take a little break.